Okay, hello everyone. For our third optimization example, I again wrote it out just to make this a little bit easier. We have an 8-foot tall fence that runs parallel to the side of a house 3 feet away. What is the length of the shortest ladder that clears the fence and reaches the house? We're assuming that there are no limits on the length of the house or the ground. I guess the height of the house or the length of the ground. This is a really confusing question as well, so if you guys are given a picture on an exam, I would highly suggest drawing one because it helps you sort of visualize what you're working with. I drew it like this. It's kind of a weird question. It's like you're in your neighbor's yard and you need to get over a fence to get to their yard. I don't know. It's weird. Anyway, so we've got this fence. It's running parallel to the house. We have a ladder on this side of the fence that we're trying to lean up to get over the fence, but also to touch the house. And the fence is 3 feet from the house. So I drew kind of a side profile where we have the house is over here. This is the wall of the house. Here's our fence. That's 3 feet away from our house. We've got our ladder, and then we've got the ground. So I want to label another point on here that we don't know, and that's how far away from the fence we need the end of the ladder to be to get this. So our goal is to basically use the shortest ladder we can possibly use to do this. And we are going to use trigonometry to solve this. So from trig, we have the Pythagorean theorem. Oh, I need to label one more point, sorry. Let's label this B. And in this case, that would give us L squared, our hypotenuse, is equal to B squared plus, in this case, our other length is 3 plus x. So 3 plus x squared. Okay, and we also have from similar triangles, if we look here, this is a right triangle, and this is a right triangle, and they share all of their angles. So this triangle has all the same angles as this larger triangle, so we know that their sides have to be in direct ratio. That is, B compared to 8 needs to be the same as 3 plus x compared to just x. So to write that out a little bit better, we have B is to 8 as 3 plus x is to x. So our big height is to our little height, as our big base is to our little base. All right? So we want to minimize length, which means we need length to be in terms of one variable. And right now it's in terms of both b and x. So we're going to solve for b using the second equation and plug it into our first equation to have this as equation of just one variable. All right, so from the similar triangles, we have b is equal to 8 times 3 plus x over x, which I can rewrite as 24 plus 8x over x, which I will again write as 24 over x plus 8. That'll just help us when we're actually taking the derivative. And we're going to plug that b value into our L squared term. So we can rewrite L squared as 24 over x plus 8 quantity squared plus 3 plus x quantity squared. All right? And this is a function, so this is L squared of x. It's a function of x, which means we can maximize this function by finding some value of x that makes it maximal. All right? And then that value of x will help us determine our length. Well, I guess, yeah, we'll just plug that value of x back in to get our length. You guys might be saying, well, this is actually the length squared, so we need to solve for just L first, but that's not true, because we're not maximizing, we're minimizing. But if we minimize the length squared, then it's also going to minimize the length, right? So if I have, I guess you could think of it as an actual square. So if I have a square, and it's length times length, if I minimize the area of the square, I'm also going to be minimizing the length. Okay, so that's what we're doing, which means we'll just take the derivative of this length squared function. All right, so we're going to do L squared prime. It's kind of a weird way to write it, but I'm sure you guys can follow. So first of all, this is a function within an outer squared function, so we'll need to chain rule. We'll bring down our 2, leave the inside, so 24 over x plus 8. Decrease our power to 1, and then take the derivative of the inside. The derivative of 24 over x is negative 24 over x squared. You guys can confirm that. I'm hoping at this point you guys are pretty comfortable with that. And the derivative of 8 is just 0. So that's that for our first part. And then we add it to, this is another function within a function. We bring down our 2, leave the 3 plus x. But the derivative of our inner function is just the derivative of x, which is 1. So we don't really need to worry about a chain here. Okay, so this is a really disgusting function, but at this point what I would do is just set it equal to 0 and solve for x in Symbolab. Right, there's no point in actually solving this by hand. So if I set this equal to 0 in Symbolab, I'll get x is approximately equal to 5.77. All right. Now we need to just confirm that this is a minimum value. And in this case, because I don't want to take a second derivative of this function, it's just going to get more disgusting. I'm going to use the first derivative test. Which, if you guys remember, was where we used a number line and tested values on either side. So we have our x is approximately equal to 5.77 as our critical point. And we're going to plug in values from the left, let's say x equals 5, and the right, let's say x equals 6. And if you plug those in to your derivative, of our L squared function, you get a positive value, or sorry, I lied to you, a negative value at x equals 5, and a positive value at x equals 6. So that's saying the slope of our length squared function is negative on the left-hand side and positive on the right-hand side. So we know that this is a local minimum. Right, our L square function is going down, flattening out, and then going up, so it has to be a local minimum there. All right, so that's our local minimum. We just need to find our actual length value. So we know L squared of 5.77 is our minimum, and that's equal to approximately 224.77. Technically this is feet squared, but that doesn't make a lot of sense, so we're going to ignore units for right now. This gives us, if we take the square root, that the length of 5.77 is approximately the square root of this guy, so 224.77 square rooted, which is approximately equal to 15 feet. So, the minimal length of the ladder that will fit the solution is 15 feet. So you need at least 15 feet, and you'd have to put it approximately 5.77 feet away from the base of the fence. Alright, so that's your guys' final optimization problem that I'm going to go over. Hopefully that makes sense to you. Please email me if it doesn't. See you guys later.